In the last lecture we talked about PV diagram for a real substance. In this lecture we'll be talking about phase diagram, okay, phase diagram of a real substance, in which we talk about how substances undergo phase transition from one state to another state as we change temperature and pressure. So any matter can exist in three phases: solid, liquid, and gas, depending on its thermodynamical condition. A transition from one phase to another phase ordinarily requires phase equilibrium between two phases, and for a given pressure this occurs at only one specific temperature. We saw in the last lecture in PV diagram. So here there is this vapor phase. Oops. We have vapor phase in this region, and we have liquid phase in this region. So this is the vapor saturation curve, this dashed line, okay, and that's the saturation point. Okay, as you compress the gas along these isothermal lines, it will be compressed up to this point. Okay, up to this point that would be in gas phase or vapor phase, and at that point it will undergo the phase transition. Okay, it will be converted to liquid, and in this line, along this line, there would be mixture of liquid and vapor. They will be in equilibrium, and at this point the the vapor would be now completely transformed into liquid phase. So at this point everything will be now vapor. Okay, so before it goes from liquid to completely to vapor, from vapor completely to liquid phase, it needs to be in this equilibrium mixture. So we can represent these conditions on a graph with the axis P and T, called this phase diagram. So each point on the diagram represents a pair of values P and T. So any point you look on this diagram, it represents a specific value of P and T. Okay, so here it would be P and T, here it would be some other P and T, pressure and temperature, here it would be some other pressure and temperature. So you get different pressure and temperature for different points on the PT diagram, and only a single phase can exist at each point in the phase diagram, except for the points on the solid line where two phases can coexist in phase equilibrium. Okay, like here all the points in this region represent the solid state, whereas in this region, in this dark blue region, all the points, all these PT points represent liquid phase, and here all the points in this region represent vapor phase. So only one phase exists in these regions, except along these lines. Okay, so we have these three curves along which you can have two states in equilibrium. So the fusion curve, which is this straight up line, it separates the solid and liquid areas, and represents possible conditions of solid liquid phase equilibrium. Okay, all the points here denote the condition for the existence of solid liquid equilibrium. Okay, on this side it's all solid, on this side all liquid, but along this line you choose a value of P and T that if that value, if the coordinates lie on this line, then that would represent the solid liquid equilibrium. Okay, you can get both solid and liquid at that particular state. Likewise, the vaporization curve, which is this one, separates the liquid and vapor areas, liquid on the top and vapor on the bottom, and the sublimation curve, which is this one, separates solid and vapor areas, solid on the top here and vapor on the bottom here. So all the three curves meet at a triple point, which is this blue dot, the only condition under which all phases can coexist. Okay, in this condition, if you choose this particular pressure and temperature, you get all the three states. Okay, so that's the condition where all the three states, liquid, vapor and solid, can coexist, like we talked last time, the triple point of water to calibrate a thermometer in Kelvin scale. So if we add heat to a substance at a constant pressure, it undergoes a series of states, okay, represented by the horizontal line A, this one. So we are increasing the temperature along this line, and as we increase the temperature, keeping the pressure constant, it undergoes through all these different states. So initially it's in vapor phase. Actually, we need to go from left to right because we are increasing the temperature. So initially it's in solid phase, and then it goes to liquid phase, and it crosses this vaporization curve, and it goes to the vapor state. So the melting and boiling temperatures at this pressure are the temperature at which the line intersects the fusion and vaporization curves respectively. Okay, so at this temperature there would be melting of substance from solid to liquid, and then at this temperature we get vaporization of the liquid. Okay, so when the pressure is constant, heating transforms a substance from solid directly to vapor, like we see here in this line along PS, or this S line. When we heat the substance, a solid substance, it undergoes the phase transition from solid directly to the vapor without undergoing through the liquid phase. Okay, which we call a sublimation process. Right? So that's why we call this line the sublimation curve. So at any pressure less than the triple point pressure, no liquid phase is possible. Like if you look at the pressure that is below that, so that's the triple point pressure. Okay. And if you look at the region below that triple point pressure, you don't get any liquid. Okay, everything is either solid or vapor. So for example, the triple point pressure for carbon dioxide is 5.1 atmospheric pressure. Okay. So at normal atmospheric pressure, solid carbon dioxide undergoes sublimation. So there is no liquid phase at this pressure. When you leave some carbon dioxide at normal atmospheric pressure, you see that the solid carbon dioxide gets vaporized without undergoing to the liquid phase. Okay, because under any pressure below critical pressure, it can easily go to the vapor phase. If we look at line B, this vertical line, we see that it's a constant temperature line. So temperature along this line is constant, which is TB, and along that line the material passes from vapor to liquid and then to solid at the points where this line B crosses the vaporization curve and fusion curve respectively. Okay, when you increase the pressure along this line, the vapor becomes liquid as it passes through this vaporization curve, and liquid becomes solid as you increase the pressure when it crosses this fusion curve. Okay, and if we look at this line D, so line D is again constant temperature line, and if we compress the object or substance at lower temperature, so here the temperature is low, this line is at lower temperature than this line, so at some lower temperature we are compressing the substance by increasing the pressure. So when we do that, the material passes from vapor state to solid state. Okay, at this point where it crosses this sublimation curve. So as it crosses the sublimation curve or sublimation line, the material undergoes phase transition from vapor state to solid state. So we saw in the PV diagram of the previous figure here that a liquid vapor phase transition occurs only when the temperature and pressure are less than critical points. Okay, that's what we saw here. So only below that temperature we saw there is transition from liquid to vapor. So as we increase the volume, we see there is phase transition. So a gas at a pressure above the critical pressure does not separate into two phases when it is cooled at constant pressure along a horizontal line above the critical point. So there is no difference or no distinction between liquid and phase above this critical temperature. Okay, and exactly at the critical point they all become zero. So the distinction between the liquid and phase disappears above this critical point, or in other words, the properties of the material for liquid and gas, such as density and compressibility, becomes almost same for all the phases, both liquid and vapor phases. So both liquid and vapor phase act as the same kind of phase, because now there is no distinction in density and compressibility for those states above this critical temperature. Okay, so that's about the phase diagram for this real substance. And this phase diagram is a two-dimensional diagram where we plot pressure versus temperature. Now sometimes it is more informative if we draw three-dimensional diagrams instead of two-dimensional diagram, because three-dimensional diagrams have more information than two-dimensional phase diagram or the PV diagram. And we know that the thermodynamical variables P, V or T, so each of these can be written as the function of other variables. Like this can be written as the function of V and T, this could be written as the function of P and T, and this could be written as the function of P and V. Okay, so if I consider P and P and let's see, yeah, so P and let's see, this is P and V as the coordinates on some plane, then temperature would be given by the third axis. Okay, third axis above the P and V plane. So then this temperature would be some kind of surface above the P and V. Okay, it's like mountain. Okay, so you have this x direction and you have this y direction. Okay, and then you have some z direction. Okay, this z direction would be the surface on the mountain. Okay, likewise here T would be the surface on the over the PV surface. So the equation of state given by F of PVT of any material can be represented graphically as a surface in three-dimensional space with coordinates P, V and T. So visualizing such a surface can add to our understanding of the behavior of material as various temperatures and pressures. So we can see in the figure this PVT surface. So the light lines, these gray light lines, this one, okay, all these lines represent isothermals. So they are all the lines at some particular temperature. So this one is for T4, this gray line, this gray curve is for TC, which is critical temperature. This other one is for T3, and this one is for T2, and this one is for T1. Okay, and if we project them onto some PV plane, then we get the diagram similar to the phase diagram that we saw before. So if I take cross section along these isothermal planes, so we can call this isothermal plane, this is another isothermal plane, this is another isothermal plane. Okay, I just take the cross sections and then just overlap the isothermal planes one over the other. Okay, just in other words, you can just project them on a single plane. Something like if you just squeeze this surface, okay, into a single plane, just squeeze this front side and back side into a single plane, then you will see this kind of PV diagram. Likewise, if you just squeeze this left and right into a single plane, then you get this kind of diagram, which is the PT diagram. Okay. So, or if you can, if you want, you can also consider this to be some section of this plane along this line. Okay, if you take a section along this line, you get this kind of PT diagram. Okay, you take a section, you get that PT diagram. Likewise, if you take section along this plane, then you get this diagram. So if we look at this three-dimensional surface, we see different lines. So let's consider one of the lines. Let me use different color here. So let's use this one. So let's look at A, B, C, D, E, F line, which is this one. So let's consider this line A, B, C, D, E, and F, which is that. So consider this line. So that line represents constant pressure heating. Okay, so we are increasing the temperature as we go along that direction. So we are going from A to B by increasing the temperature or by heating the substance, and then we go from B to C, and then C to D, D to E, E to F. Okay, so as we heat the substance at constant pressure, so this path is along a specific pressure. So it's like we are considering this particular pressure. So pressure is increasing in the upward direction, but we are considering this section. That means the pressure is constant. So we will see that if we move along that, we will see the melting occurs along BC. So from B to C, there would be melting of the substance. So from A to B, it would be in solid phase, and at B we will have phase transition. Okay, and then from B to C there would be equilibrium of solid and liquid phases. We'll have both solid and liquid phases, and at point C the phase transition completes. Now everything will be in liquid phase. So between C and D we have everything in liquid phase. And then at point D, as we increase the temperature, the liquid undergoes phase transition. It will be partially transformed to vapor, and there would also be liquid. So there would be equilibrium between liquid and vapor phase in this region, and the phase transition completes at this point E. Okay, and from E to F, now everything would be in gas or vapor phase. When we move along this line, as we increase the temperature, we see that it's moving, it's also moving from left to right. Okay, so we are moving gradually from left to right. That means there is also increase in volume. So as we increase the temperature, there is also increase in the volume. Now along the line GHJKLM, which is let me use a different color here to denote that. let's use that. So if we move along this one, so G, H, J, K, I'm not drawing the line straight, so it's hard to draw a straight line on a PowerPoint. Okay. So if I move from G to M, that corresponds to the isothermal surface or isothermal process, and it's isothermal compression because we are moving towards the decreasing volume. So we are compressing the gas. Okay, so you see that as we move along this line, we are moving from right to left, and as we move from right to left, it's gradually ascending. Okay, it's ascending. That means the pressure is increasing, and as we go from this point to that point, there is a drastic ascending of pressure. That means in order to go from liquid phase to solid phase, you need to apply lots of pressure. So it takes lots of pressure to compress the liquid, and it takes even more pressure to compress the solid. Okay, so when it's in solid phase, you can compress the solid by only small volume for this large pressure, large increase in pressure. So along that line, so there would be liquefaction along line HJ. So as we go along this line, like we talked about this in the last lecture also, when we go from G to H, we are compressing, and at H it undergoes phase transition from vapor to liquid. Okay, so we have here vapor, and it undergoes phase transition to liquid, and along this line H and F there would be equilibrium between liquid and vapor phase. Okay, that the transformation is not complete yet, but at C the phase transition is complete. Now everything would be in liquid phase. Okay, and as we increase the pressure, the liquid now transforms to solid at point K, and between K and L we have equilibrium of solid and liquid, and at L here the transformation completes, and now everything after L would be in solid phase. And once it's in solid phase, again, like I said before, it would be really hard to compress the substance. Just to compress it by a little bit, you will need to apply large pressure. So finally, if we look at the line NOPQ, so let's again use a different color here. So let's see, what color should I use? Let's use this purple color. So NOPQ is this line. Okay. NOPQ. Okay, that should be a straight line, but I can't draw a straight line. So again, this is isothermal process. So when we go from N to, this is at lower temperature. So all these things we talked before, the one that we talked before is at higher temperature or some higher isothermal process. But here we are talking about isothermal process at some lower temperature. So as we go from N to O, there would be phase transition occur at point O, and at the lower pressure we won't see the liquid phase. Unlike up here, we don't see the liquid phase, so it undergoes directly from vapor phase to solid phase. So there would be equilibrium between solid and vapor phase in this, along this line. Okay, and then at this point P, the transformation completes, and then everything would be now in solid phase. Okay, just like the example for this is in formation of snowflakes or frosts. Okay, so during the formation of snowflakes, there is transition from vapor directly to solid, which is kind of ice, and that occurs when it's below the triple line. Okay, in case of the two-dimensional graph or two-dimensional picture, we were talking about triple point. Okay, in the previous picture we talked about triple point. So at triple point you don't get below the triple point you don't get the liquid phase, you only have solid and vapor phase. So now instead of calling triple point, so because this is a three-dimensional picture, so we call this triple line. So this is a line. So if we had in the previous picture, there's only one single dot here, single point here, but now as we expand this along this increasing volume, we see the triple line. Hello. So here is a PVT surface for an ideal gas, which is much simpler than the previous PVT surface. So in this PVT surface we have volume and temperature along these two axes, and then pressure is represented by the surface. Okay, this surface over this volume and temperature plane. Now if I cut along this surface, then I get a PV diagram for this particular temperature. Okay. If I cut along this surface, or just cut along this plane, then I get another PV plane. Okay, I can do the same thing here. I can just cut the surface along this plane, I get another PV plane. And if I overlap those constant temperature planes over each other, then I get this kind of PV diagram, okay, with this isothermal curves. So each cross section will give us one particular plane for one temperature, and if we just overlap them, we get a bunch of isothermal curves. Or you can say that if you just squeeze this plane along this temperature axis, just press that and squeeze into one plane, then you will see this kind of PV plane. Likewise, if you squeeze this three-dimensional surface along this volume and just make it flat, then you will see this kind of PT diagram. Or in other words, you can also say that if you just cross it or cut it along this line or this plane, okay, it looks like a line, but it's if you just cut it along that line, it will be a plane. So cut it along that line, so you get a plane. You cut along this line, you get a plane. Okay, you get a section. And if you just overlap each of those sections over each other, then you get this PT surface, okay, or PT diagram. So let's look at the PVT surface for water. So this is exactly same kind of diagram that we saw in the beginning. We have vapor phase or gas phase in this region. We have liquid and vapor phase in this region. This is triple line, and below the triple line we only have solid and vapor. Okay, so we can when we compress the gas, we go from vapor phase directly to solid phase. Okay, through this equilibrium state. And above the critical temperature, you see now it's all in vapor phase. Okay, so there is no distinction between liquid and phase. There is both liquid and gas phase, but you cannot actually distinguish whether they are liquid or gas. They have similar kind of properties. So that's about the phase transition and PVT surface or PVT diagram. So next part we will talk about expansivity and compressibility. So let's move on to the next topic. Okay, so let's talk about expansivity, which is denoted by Greek letter beta, and compressibility, which is denoted by Greek letter kappa. Okay, so let's suppose some substance that has some specific volume V. Consider some substance with specific volume V. Again, V, this is the specific volume, which is this big V over N. So when the temperature or pressure of the substance is changed, it shows that it will respond to the change in temperature or pressure in certain way. Okay, so to explain the response of the substance to change in temperature or pressure, we use these terms, expansivity and compressibility. That's why they are also called response functions. Okay, so let's define what these things are. So this expansivity is basically how the substance responds to change in temperature at constant volume. It is defined as 1 over V dV over dt at constant pressure. Again, how the volume is changed as the temperature is changed at constant pressure. Likewise, compressibility is defined as how the volume is changed as you change the pressure, keeping the temperature constant. Okay, and this negative sign implies that the response function, or the way the volume responds to the pressure is up in the opposite direction. In other words, as you increase the pressure, the volume is decreased. Okay, or vice versa. If you decrease the pressure, volume is increased. That's why we have negative sign there. Now let's look at these response functions for an ideal gas, which is represented by this equation. So this equation is the equation of state for ideal gas, or we can also write this as V is equal to RT over P. So beta for ideal gas is 1 over V ddt. V is RT over P, okay, at constant pressure, so 1 over V. So we are keeping pressure constant, so we can pull this pressure out, and also this R is the gas constant, we can pull it out, so R and P out. So then we have del T, and we're taking derivative of T, okay, at constant pressure. So the derivative of T is, with respect to T, is 1, okay, so we have this thing is 1, so R V times P. And we know from this ideal gas law that PV is equal to RT, so we can replace this VP by RT. You cancel R and R, so that means beta is equal to 1 over T. Okay, so that's the expansivity for ideal gas. Now let's look at the compressibility for ideal gas. Compressibility is kappa is negative 1 over V ddP. So it's volume here, so we can write volume as RT over P, and that's at constant temperature. So since the temperature is constant, we can pull temperature out of the derivative, so 1 over V, both R and T are constant, so that means the partial is with respect to P would only apply to this 1 over P. So negative RT V. Now when you take the partial of 1 over P with respect to P, you get minus 1 over P squared. Okay, and so this negative and negative will be positive. RT, we can replace RT by PV, so write PV for that, over V, and 1 over P squared. Cancel V and V, cancel this P and one of the P's here, so kappa is equal to 1 over P. So the response function in terms of change in temperature, which is expansivity, is given by reciprocal of temperature, and the response function of a substance in terms of change in pressure is given by the reciprocal of pressure. So that means we can conclude that the higher the temperature, the lower is the expansivity, or that means the expansion gets slower and slower as the temperature increases. That's what this indicates. Okay, likewise here, the higher the pressure, the lower is the compressibility. That is, it gets harder and harder to compress an ideal gas as the pressure is increased. Okay, now in the next lecture we will talk about the response of volume to temperature and pressure for solids and liquids. We talked about ideal gas, but now next time we'll talk about the same thing for solids and liquids. Okay, so that's all for this lecture.